So chapter 5 is about chemical reactions and stoichiometry. Before we begin the chapter, at the comfort of your own homes, I invite you to watch this fun video. Just search on YouTube, chemical party, or just click on this link. I swear it's fun. But anyway, chemical reactions basically explain what's happening all around us, be it natural phenomena, such as, did you know when the French actually gave us the Statue of Liberty before, it was a little bit light brown in color? That's because the Statue of Liberty was actually made out of copper. Okay? Now, the surface has reacted with moisture over time in this balanced reaction. And while most of the Statue of Liberty is still copper, on the surface you actually have hydroxides and carbonates of copper instead. Okay? You can see on the right of it, we're still at New York City, the statue of George Washington. Okay, before the bust actually looks perfect, but in the late 90s or in the late part of the last millennium, it looks like he was punched on the face. Okay, and that's just because calcium carbonate, which composes the statue, has reacted with sulfuric acid in acid rain. Okay, so we can also solve natural phenomena like that, or I guess natural problems like that, such as also corrosion. Okay, when infrastructures fail, say for example when iron in bridges reacts with moisture in the air, you have rust formation, which actually sees the fall of bridges or the collapse of these bridges and other infrastructure. And then you can also explain other phenomena such as combustion, especially if you have a gas range stove, with how those fires are produced or how your food is being cooked. Okay, so one question is, if I ask you to count how many Skittles there are in this jar, so one thing I would have done will be to open the lid, take out each Skittle one by one, and then count them one by one. Okay? Now, what if this was a larger jar? Okay? So it would have been harder to count the Skittles one by one, and probably we need another unit, or we need another way to count them. So the same thing can be expressed for subatomic species, atoms, and molecules. So up until this point, we have been discussing one molecule, one atom, a few atoms, one electron, two electrons, a few of them, okay? But in reality, all of these atomic species, or subatomic species rather, and atoms and molecules are very light, meaning they're not even gonna be weighing as much as 1 microgram. Okay, so let's say for example a 50 milligram drug actually contains more than quadrillions of atoms. Okay, now how do we actually count those atoms when we are looking at stoichiometry, when we're looking at a study in chemistry which actually deals with chemical reactions? So in able to process those large numbers, we have to work with another fundamental SI unit, amount of substance, which is defined as the mole, okay, and has this abbreviation. The mole is just simply how many carbon atoms there are in 12 grams of pure carbon-12 diisotope. And the answer to that question is there are exactly 6.0221476 times 10 to the positive 23. This number is Avogadro's number. That was the definition at least before 2009. Before 2009, everything was like defined with respect to that. Now, in 2000, did I say 2009? I meant 2019. So in 2019, the definition was slightly changed. And now, moles are actually the amount of substance consisting of exactly 6.0221476 times 10 to the 23 entities. Let's say, for example, if you're looking at one molecule of water, then you have if you're looking at 1 mole rather of water, you're then looking at 6.022 times 10 to the 23 molecules of water. If you have, for example, 1 mole of aluminum, then you're looking at 6.022 times 10 to the 23 atoms of aluminum. Okay, that being said, you actually have these mass equivalents for all of those number of moles for the specific elements. And these values are something that are just arbitrary. We actually get them straight from the periodic table. So in the periodic table, in chapter 5.2, we have mentioned that to calculate isotope average masses, we just have to take into account the percent abundance of each isotope, as well as the atomic masses of each of those isotopes. Okay, and then that number that we see here in the periodic table is the average atomic mass, which has a unit U, or for 1 atom of this element. Now, that being said, if we're going to actually have this number with units of grams, okay, if the unit of this number, again, 50.9415 for vanadium, was grams, then that's actually the mass of 1 mole of a substance. So since it's still an element, we're still going to call it atomic mass, but some textbooks actually call it molar mass to basically indicate that that is the mass of 1 mole of an element. Now, the term molar mass is actually more generic. We use it more for compounds. But for this chapter, we're going to use them interchangeably. Atomic mass and molar mass, at least for the elements. Now, all of these basically have different masses, but they all are equal to 1 mole. Now, the definition of the mole does not have to be limited to number of atoms. You can also have 1 mole of photons. A mole of photons is basically 6.022 times 10 to the 23 photons. You can have 1 mole of electrons, so 6.022 times 10 to the 23 electrons, or mole of molecules, whatever actually. In fact, you can actually have a mole of money. Okay, now I'm not going to really work on this one. I want you to do this on your own. This will actually help you keep up again with dimensional analysis, which we actually need for this chapter. But I'm just going to tell you right now that the answer to this problem is each person will get $90 trillion. Okay, so wow, that's actually your money, and again, that's per person. So imagine if you were 1 mole rich. Anyway, I did say that we are going to look at dimensional analysis at this chapter. So let's actually try to look at some problems. So, say for example, you're given the mass of the substance, be it an element or a compound, but our focus right now is an element. So what you want to do is, using the atomic or molar masses provided in the periodic table, we can convert those values into moles, okay? And mole values, you can actually convert them into atoms for elements or molecules for compounds and so on and so forth. But let's look at elements first. A small gold bar weighs 421 grams. How many moles of gold are in the gold bar? Okay, so for this one, we're just converting grams to moles. Okay, and we see here that for every 421 grams of gold, we want to convert that into mole. Now, again, the information that we have from the periodic table is that the atomic mass of gold is 197. 197. But again, remember that that is 197 grams of gold per 1 mole of gold. So usually all of those numbers actually in the periodic table, all of those atomic numbers are actually in the units gram per mole. Okay, they're in the units gram per mole. just an FYI. So here, we can actually use this dimensional analysis factor, to convert grams to moles. Now, before I do that, I'm going to write this as 421 grams of gold, okay? Because when we work on problems later, there will be a lot of different substances. So this is going to be 197 grams of gold, okay? And then on the numerator, we're going to write 1 mole of gold. And if we do the math, that will become 2.14 moles of gold. And again, notice that these terms will cancel out. Okay, then next we want to determine how many atoms of gold there are in a gold bar. So we can use the fact that for every 1 mole, you have 6.022 times 10 to the 23 of something. For that one, that something there is now atoms of gold. Okay, so sorry, this keeps doing that. Okay, so this one will be then 2.14 moles of gold. And then we're going to put 1 mole of gold in the denominator. And then 6.022 times 10 to the 23 atoms of gold in the numerator. And then we should get here 1.29 times 10 to the 24. 1.29 times 10 to the 24 atoms of gold. And that's basically how you work on problems like these. Okay, now I did say that people mostly use molar mass for compounds. So using the same things that we've done before with dimensional analysis, we can do this for compounds as well. But remember that compounds are actually formed from bonds with elements, okay? Elements bond with themselves and as a result form molecules. For example, if we were to find, for example, the molar mass of CH4, okay, so that we can find out how many moles there are per gram of CH4, or within a specific gram of CH4, methane. So we observe just the law of conservation of mass, meaning the bonds or the elements that are actually being used to form methane come from carbon and for hydrogen. So therefore, the atomic masses of 1 carbon and 4 hydrogens added together should give the total molar mass, or in some old textbooks, molecular weight of methane. Okay, and then again, it's basically shown here. So that will be 12.01 grams. This is from the periodic table. And then you have 4. And then this one will be 4 times the atomic mass of hydrogen, which is 1.008 grams of hydrogen. Okay, and that's going to give you 4.0332. And then you also have, when you add them together, 12.01 plus 4.032 will just give you 16.04. Let's actually answer this one. What is the mass of 1 molecule of methane? We can expect this to be a really small number, but let's see what we get. Okay, so we are going to start with 1 molecule of methane. Okay, methane. Now, to do this, we need a molecule to gram conversion. There's no direct conversion from molecules to grams, but there's some conversion from molecules to moles, okay? Such that for every 6.022 times 10 to the 23 molecules of CH4, you actually know that there is a mole of CH4. Okay? And then from moles of CH4, we were just given earlier what the molar mass of methane is. So for every 1 mole CH4, we have 16.04 grams of CH4. Okay, and then if we do this math, the answer will be careful with the answer, by the way. It should be a really, really small number because it's just one molecule. 2.66 times 10 to the negative 23 grams, okay, of methane. And again, just watch the terms cancel out. Okay. Now, another way to express, I guess, another way that we actually are looking at for this chapter, which will be useful for some problems, are percentages of the components in a compound. So there's actually two kinds of percentages. Composition percent, which is the percent of each element in a compound based on the total number of elements in the compound. Let's just say, for example, according to this cartoon, you have 67 almost percent of hydrogen, and that number is just derived from knowing the fact that you have 2 hydrogen atoms, okay, divided by 3 total atoms, okay, meaning 1 oxygen and 2 hydrogens, okay, and then this is times 100%, so that should give you 66.67%. Okay, now the same thing can be done with the one oxygen atom, okay, over 3 atoms. And this will give you 33%. Now another thing that you can do to solve for 33% will be to subtract 66.67 from 100, because keep in mind that the percent of hydrogen plus the percent of oxygen is equal to 100%. Okay, now if you have percentage by mass, as you can see here for the composition percent, it looks like hydrogen is the main contributor to water, but to the percent by mass, actually it's a different story. It's actually, we actually see here that oxygen contributes more to the mass of water. And this value is basically calculated by the following. So as the name implies, mass percent, so we have to get the total mass, for example, of hydrogen. Okay, so to do this for hydrogen, what we just do is how many hydrogen atoms do we have? So there's 2 hydrogen atoms. And what's the molar mass of hydrogen? 1.008 grams. Okay, that's what the mass, molar mass of 1 hydrogen atom. Okay, and then divided by the total, and then divided by, then we will divide it by the molar mass of water. And the molar mass of water is actually 1.008 times 2 plus 16. Okay, so this should give you 18.016 grams. That's the molar mass of water, gram per mole. Okay, so this, for this one for water, this will be 18.016 grams. Okay, and then if we multiply, if we divide both sides, it's going to be times 100%, and this is going to end up to be 11.19%, which is basically what we have here. Now again, for percent oxygen, we can just subtract 11.19 from 100, or we can do it the hard way and use the percent oxygen is equal to 16.00 grams. That's the molar mass of oxygen divided by 18.016 grams, the molar mass, and of water. And here you get 88.81%. Okay.